Now let's get started. Today we are going to be studying Joule's law, specific heat constants, and we are going to be introducing you to the concept of entropy. Okay, so let's get started. Okay, what is a real gas? In a real gas, by the way, can you see the motion of my cursor? Are you able to see this motion? Can you guys see the motion of the cursor?
Yes, sir.
Okay, good. So in a real gas, volume of molecules is finite. So what do I mean by that? Gas is a phase in which, the spaces between each molecule is large. Of course, in solids, the molecules are stacked together. They are placed together in some structural way. So that is what we call solids. In liquid form, the molecules go further apart, and in gaseous form, the molecules go very far apart. Okay, so if you look at a gas and you try to calculate the volume of the gas, you will realize that the most of the volume is because of the spaces between the molecules, right? And if your pressure is low and temperature is large, means the molecules will be very far apart from each other. So in a real gas, molecules have finite volume, meaning that, of course, let's say in a gas filled in a container, most of your volume are just empty spaces, but of course, molecules also occupy some volume. And also, the intermolecular forces are present in a real gas. Why? Because molecules are big enough, let's say they are not extremely small, and they can have some forces between them, some electrostatic force or gravitational force or whatever. And you have to understand that with each force, there is a potential energy involved. Let's say with spring, there's spring potential energy. With gravity, there is gravitational potential energy. So with every force, there is potential energy involved. So you have intermolecular forces. So you may have electrostatic potential energy in the form of intermolecular forces. Okay, so and also we also know that these effects, meaning that the volume of the molecule is finite, it's not negligible, and intermolecular forces are present in the molecule. These effects become prominent at low temperature and high pressure. Why? At low temperature, your kinetic energy is low, so it means molecules are going to be affected with intermolecular forces of attraction, and also at high pressure, low volume. Because when the volume is low, it means the volume of the molecule is more important now. Let's say if the molecules were not very far apart, if the pressure is high, right, and the temperature is low, if the molecules were already not very far apart, so it means the volume of the molecules cannot be low in comparison with the spaces between the molecules. You see what I'm trying to say? So you have some spaces between the molecules and they are extremely large, but at low pressure, these spaces have become small. So when these spaces become small, so the volume of the molecule itself becomes important. And also intermolecular forces become important. Therefore, the internal energy is a function of temperature and volume. Of course, your internal energy, which is kinetic energy and some potential energies, is going to be a function of temperature and volume. Of course, kinetic energy is going to be a function of volume, temperature. I told you, more temperature you have, it means higher is the kinetic energy of the molecules in the gas. But if the gas is real, means intermolecular forces are important and volume of the molecule is not negligible, then of course you can see that your internal energy is also going to be a function of volume. And when the volume is low, this is going to be a strong function of volume, because intermolecular forces are going to have some potential energy associated with it. So it means the internal energy of your gas. What is internal energy of your gas? Any electrostatic potential energy or kinetic energy or vibrational energy or torsional energy, everything. All of these are called internal energy of a gas. It is actually dependent on temperature and volume in a real gas. Okay, what happens if you have an ideal gas? Let's see. For an ideal gas, volume of molecules is insignificant, because in an ideal gas, the molecules are extremely far apart from each other. So it means their volume in comparison with the spaces between, the average spacing between the volume becomes really important, is really negligible. Let me repeat. Because in an ideal gas, the spacing between the molecules is extremely large. So this is why the size of the molecule itself becomes negligible. Why? Because the spaces are so large. And intermolecular forces are going to be negligible. Why? Because the molecules are so far apart from each other. So in that case, your internal energy is only a function of temperature. Why? Because the volume is extremely large. A gas starts to behave like an ideal gas when the molecules are sufficiently far apart. That is, at low pressure and high temperature. Means when the pressure of your gas is low and temperature is high, you can understand that, of course, your objects are going to have a lot of kinetic energy, so they are just going to move away from each other. And low pressure, it means the volume is large. It means the intermolecular forces are negligible, and volume of the gas itself is negligible in comparison with the spacing, average spacing between the molecules. Okay. It's just like, in astronomy, or let's say when we are talking about galaxies, the spacing between our planets and stars is so large that they can be considered point masses. Of course, they are huge masses themselves, but the spacing between them is so large that they can be considered point masses. Similar is here. The spacing between the molecules is so large that their volume is insignificant. Okay, so this is why in an ideal gas, your internal energy is only a function of temperature, not volume. Why? Because volume is so large, the intermolecular forces are not going to have any contribution. So this is why the internal energy is going to be a function of temperature only. So what in the loose sense, it means in soft words, I'm trying to tell you that internal energy in an ideal gas is mainly the kinetic energy. Means all the other energies, let's say electrostatic forces of attraction and the electrostatic potential energy, all these energies are negligible. So in an ideal gas, your energy is mainly kinetic. So it means in an ideal gas, the internal energy of the gas is mainly kinetic, and it's a function of temperature. Okay, please let me know if you have any question. Otherwise, I'm moving on. So this is called Joule's law. Joule's law says that in an ideal gas, your internal energy is a function of temperature. Please let me know if you have any question. Otherwise, I will move on. Okay, specific heat capacities. Let's see. I tried to go through this topic in the last lecture, but I realized that probably you would need a little more time in adjusting to this idea. Okay, so forget about we are doing thermodynamics. Suppose you had a block of ice or whatever, and you were trying to add heat to it. You know its temperature is going to be raised. So heat added to a system raises its temperature. That's what we know. That you add heat to it, you put it on your stove, and the temperature of that object or that system will be raised. Okay. Of course, the raise in temperature will be small if mass is large, right? You are adding a fixed amount of energy, which is fixed. So if mass is large, so it means delta T is going to be small. This is very intuitive. You can understand it, right? And also, for a fixed mass, let's say if you add some energy, the temperature that you are going to raise is also going to depend on this constant specific heat. if your specific heat is large, then the temperature change is also going to be small, right? Let's look at this expression. Del Q, del capital Q is equal to MC del T. It means if your specific heat is large, then your delta T is also small, is actually small. So specific heat is kind of, it's telling us that what is the capacity of the system to store the heat energy. For example, capacity of storing energy in metals is rather low. Why? Because you store, you heat a metal, its temperature raises very quickly, and if you leave it, its temperature comes back to its equilibrium very quickly, right? Metals cool down very quickly, metals heat up very quickly. So it means they can't store a lot of energy. So it means their specific capacity is very low. C. Specific heat capacity is low. C. So what are the materials with high speed specific capacities? Ceramics are materials. Ceramic are the materials which have large heat capacities. You know what ceramics are? Ceramics are, all you all have seen the bricks from which we construct a house, construct a wall. So those bricks, those red color bricks, that is kind of a ceramic material. And of course, ceramic materials have large heat capacity. So when you heat them, it takes a long time for their temperature to rise. And when you stop heating them, it takes a long time for their temperature to go down because they store a lot of energy in them. This is why in the summers, your walls never cool off, even at night. Of course, during the day, the sun is, baking or heating your walls, the ceramic walls. But even at night, when there is no sun, the temperature of your wall does not go down because these are made from ceramic materials. This is why when sometimes it rains in the summer, let's say even if it rains for 2 or 3 hours, even when if it rains for 2 or 3 hours, so the environment of your house will become comfortable for at least 2 days. Why? Because the temperature of the ceramic walls has gone down. So it takes some time for it to heat again. Somebody had raised hand. Please speak up. I forgot the name. I think it was Arkam who had raised hand. So please speak up. Okay, so we move on, and now I write the same equation and divide the whole thing with mass. So this becomes heat added per unit mass. So this mass will be gone, so it becomes C delta T. As mentioned previously, heat added to a system depends on the path. So let's now come back to thermodynamics. In thermodynamics, heat added to a system depends on the path. If it is a constant pressure path, at what pressure you are adding, if the pressure is changing, pressure and volume are changing, something like that, right? So your del Q, it is del Q, it's not dq. Why? Because how your pressure and volume change is going to it's going to change how much heat was added. So del Q is a path function also. So of course there are infinite ways by which you can add heat to your system. You can keep your pressure constant, you can keep your volume constant, you can keep your entropy constant, you can keep your temperature constant. So there are many ways you can add heat. There are actually infinite ways, but we are going to be interested in only in two ways of adding heat: constant volume process and constant pressure process. Why is that important? Let me show you why. Sometimes your system is isolated, so it means it is closed inside a box. So that is called a constant volume process. So of course, if you heat a gas in a fixed cylinder, let's say you all have seen a cylinder from which we burn the gases. The gas cylinder which you go and take out and fill the gas. The same cylinder which you have in your CNG cars. So let's say if you close the valve of that cylinder and you start heating that cylinder, it means that is a constant volume process. Your gas is not going to change its volume. It's going to remain constant. So in that case, let's go to first law of thermodynamics. First law of thermodynamics says that the change in internal energy comes from the heat you add and the work you do on the system. Now you must see that I have a positive here. I'm doing this deliberately. I change the convention of first law whenever I want so that you can understand. Now you see you have a positive here. It means the work done on the system is positive. When you have a negative here, so it means work done on the system is negative. So in simple words, I can just tell you that compressing the gas increases its internal energy because you are doing work on the system. Okay. So it increases the internal energy of the system. So this is the reason why if you are considering work done on the system to be negative, so you must have a negative here. So that negative and negative become positive. If you are considering work done on the system to be positive, then you should have a positive here. Okay. Please, make sure that you understand this point. If you do not, please let me know. Okay. So del W in this case is going to be minus PdV. Why? Because when dV is negative, it means the work is being done on the system. It is being compressed. dV is negative. So it means this is negative. dV negative and negative will make it positive, and that will increase the internal energy of the system. You should also, see that this is first law of thermodynamics in specific form. Means this is specific internal energy. Also, when we are talking about this internal energy, this was specific internal energy. Remember, this was specific internal energy. Why? Because let's say if this was internal energy, it should also be a function of mass, because if larger the mass you have, larger the molecules you have, larger the energy you have. But at the moment we are talking about specific internal energy, means energy per unit volume. This is also energy per unit volume. Now we are writing the first law of thermodynamics, in specific form, means everything has been divided with mass. So what the first law of thermodynamics says that the change in internal energy of your system is equal to the amount of heat you add and the amount of work you do. Of course, the amount of work can be written like this. Excuse me. So if the volume is fixed, if the volume of the container is fixed, so dV is zero. So it means volume cannot expand. You see, suppose you are adding gas to a system in which the volume can increase. You know that when you add some heat to it, its volume is going to change. It is going to expand. But if the volume is fixed, like, a cylinder with rigid walls, a cylinder that is sitting in your car, the rigid wall cylinder, its walls cannot move. So it means the work done by the system or on the system is going to be zero. So in that case, this thing is zero. In that case, it means any heat that you add to your system changes the internal energy of your system. So du is equal to Cv dt. You see, we do not see mass anywhere. If you do not see mass anywhere, it means we are talking about specific internal energy. And also, in most cases, the lowercase letters, this is specific volume. Remember, this is specific volume. This is specific internal energy. So in most cases, intensive properties are shown with lowercase letters except temperature. Of course, temperature is also an intensive property, but it is shown with uppercase letters. All the other lowercase letters are intensive properties. Okay, coming back. So if the boundaries are fixed, so it means any energy that you add to your system is going to change your internal energy. Okay. So of course, internal energy per an ideal gas is a function of temperature. We just learned from Joule's law. So it means I can write it as Cv dt. Okay. And now you can take your dt on the left hand side, it becomes du by dt or partial vu by partial tt. We are doing it partial because we want to make sure that the volume remains constant. So this Cv is specific heat at constant volume. Okay. The CV is specific heat at constant volume. That is equal to rate of change of internal energy as you change the temperature, right? Now we move on towards constant pressure process. What is a constant pressure process? You are boiling water in your kitchen. That is a constant pressure process. Or let's say you have a cylinder now, and the walls of that cylinders can move when you add heat to it. It can expand. So if you are heating that cylinder, or let's say that object in your kitchen on the stove, so you know the external pressure on that cylinder is atmospheric pressure. So of course, an internal pressure is also atmospheric pressure because the system is in equilibrium. So the internal pressure of the gas of your cylinder is, it should be the atmospheric pressure. Why? Because the walls of that cylinder can move now. It's a flexible cylinder. Imagine a flexible cylinder which can, which can move whenever the pressure inside becomes large. So let's say if you have a gas in a cylinder for which the walls can move and it is lying in your kitchen, so you can be sure that the pressure inside is atmospheric pressure. Because if the walls are in equilibrium, it means the external pressure and internal pressure on the walls is the same. Anyway, so now we have a cylinder which for which the walls can move. It can inflate. It can become, the volume can become bigger if we add heat. Okay, let's go to the definition of enthalpy. Enthalpy is specific enthalpy. Enthalpy, I should write specifics here. Specific enthalpy is equal to specific internal energy plus pressure and specific volume. Okay, so when we, let's say, take the differential on both sides, it becomes dH plus du plus P dV and V dP. Okay, but we have seen from the last slide that du is equal to del Q minus P dV. Du is equal to del Q minus P dV. Let's plug it in here. Du is equal to, so now we plug du in here. So that is equal to, du is equal to del Q minus P dV. So minus P dV will get cancelled. So we'll get del Q plus P dP. So now if your pressure is constant, it means you have a cylinder in which the walls can move now. The volume is not constant. So now you start adding heat to that cylinder. Okay. Imagine in your mind that you have a cylinder for which the walls are movable. Now you add heat to that cylinder. So you know your gas is going to expand. The volume is going to increase. And because that cylinder will try to keep its pressure constant with the external pressure. So that is a constant pressure process. So the gas will expand and the pressure will remain constant. So if you had, let's say, 1 bar initially inside your cylinder, when you add heat to it, and of course the external pressure is also 1 bar. So when you add heat to it, the gas will expand and again it will come to 1 bar. So that is going to be, because if you do not allow the gas to expand, your pressure will increase. I hope you know that. If you have a cylinder and you add heat to it and you do not allow it to expand, means the volumes are fixed. So adding heat will change your pressure also. Why? Because your temperature is changing. PV is equal to RT. We learned from ideal gas law. If you change your temperature, increase your temperature, your pressure is also going to increase if you do not allow your volume to change. You remember PV is equal to RT. If V is constant and you increase your T, it means your pressure also increases. Okay. So, but in this case, we are not fixing our volume. We are fixing the pressure. So now we fix the pressure by making sure that the cylinder walls can move when we add heat. So when we add heat to a cylinder for which the walls can move, the pressure will remain constant. So this dP is 0. So it means any heat that you add will change the enthalpy of your system. Or let's say if you measure the change in enthalpy of your system, you can measure the amount of heat added. And of course, enthalpy is also a function of temperature only. Enthalpy is also a function of temperature only. Why? Because internal energy is a function of temperature and PV is equal to RT. We learned in the last class. So you might be thinking that PV is equal to nRT. No. PV is equal to N R bar T. N R bar. Okay. But we know your N can be split into mass divided by molar mass. So PV is equal to PV, then P pressure times volume is equal to mass divided by molar mass into R bar into T, right? So we take that mass from right hand side and we bring it on the left hand side and we divide it with the volume. So that becomes specific volume. So we get P small v is equal to R bar divided by molar mass into T. So R divided by molar mass becomes R, the specific gas constant. We did this in last class. Okay, we have done this in last class. So PV is equal to RT. So this is a function of time, temperature. This is also a function of temperature. So it means enthalpy is also a function of temperature. So it means a change in enthalpy can be measured like this, Cp dt. So if your temperature changes at a constant pressure, you can measure the change in enthalpy. So of course you can take your dt on that side and you can write it like this. Why we are writing it as partial? Because we are keeping the pressure constant. Now, I would like to know how I can calculate the internal energy and enthalpy of my gas for a given temperature. Of course, you can integrate this thing on both sides, starting from zero temperature to some temperature, and of course, starting from the enthalpy at zero temperature to enthalpy at some temperature. But enthalpy at zero temperature is zero, and also the internal energy at zero temperature is zero. Absolute zero. Absolute zero means, everything is frozen. So you have no internal energy at absolute zero, minus 273 centigrade. And you have no enthalpy at 0 Kelvin. Okay. So this is the reason why when we integrate this and we integrate this, there is no constant of integration. Why? Because the constant of integration is zero, because the internal energy and the enthalpy are zero at absolute zero temperatures. So you can measure your enthalpy and internal energy from the temperature and these constants. So you see, when we integrate it, we consider them to be constants. They are constants for an ideal gas for a very large range of temperature. Now, we, in last two lectures, we have defined three constants for a gas: Cv, Cp, and R. Of course, for every gas, they are going to be different. Remember, this R is going to be different for every gas. Now, why? Because this R is equal to R bar divided by molar mass of the gas. And R bar is same for every gas, but R is not same for every gas, because for every gas, your molar mass is different. Okay. So now let's explore the relationship between Cv, Cp, and R. We know that the change in enthalpy is equal to du Vdp plus Pdv, and that is equal to du plus Rtt. Because remember, this thing was equal to RT. So if you take the differential on both sides, it becomes dH is equal to du plus R dt. It becomes like this, right? And change in enthalpy can be written as this. We just learned change in internal energy can be written as this, and RT of course remains the same. Now we take dt common from everywhere and we cancel it. So we get Cp is equal to Cv plus R, or in other words, Cp minus Cv is equal to R. We can also take the ratio between these two. For air, the ratio is gamma is equal to 1.4, the ratio between the specific heat constants. Then we can establish the relation between gamma, Cv, and R now. So of course, if this is equal, and we just found this, right? So Cp minus Cv is equal to R, Cp minus Cv is equal to R. We divide both sides with Cv. So we get gamma, we get -1, and we get R by Cv. So now we rearrange this and we get Cv is equal to R by gamma minus 1. I never memorize this relation, but I guess you should memorize it. If you do not want to memorize it, learn to derive it. It's a very simple derivation. Cv is equal to this, and of course Cp is equal to gamma Cv. Cp is equal to gamma Cv. That is going to be gamma R by gamma minus 1. I don't know. The question that you may have in mind is that why gamma is larger than 1? Why Cp is larger than Cv? Can anybody answer this question for me? It's an important question. It's a question that it would be nice if you have an understanding of this. Can you guys hold on for a minute? Is the CR here?
Yes, sir.
CR, I got your message about the link. The link never changes now, okay? I'm looking at my phone. The link is now. So this is why I never have to send you the link now. The link is always fixed. So everybody has the link. So you can always join the class. Okay. Question. Why is CP larger than CV? We can see that because gamma is larger than 1. Why is CP larger than CV? Can anybody answer this question? This is a very important question to understand. The bad thing is that you guys do not ask enough questions. You should ask questions, otherwise you will not understand. Okay, why CP is larger than CV? Let's try to understand that. First, let us go to constant volume process. We learned that if you have a gas filled in a container and the container is fixed, it means the container wall cannot move. They are rigid walls. Now you add any heat to it, will change its temperature, right? All the energy that you add will change the internal energy. Means all the energy, all the heat that you add will become kinetic energy of the molecules, right? The temperature will increase. Okay. So no work, and but in a constant pressure process where the walls of your container can move, you will expect that when you add heat, the gas will expand and volume will increase. Do you guys agree with that? But when the volume of your gas is allowed to change, right? If the walls of the containers are not rigid, not fixed, so when you add heat, the gas will expand. Is that correct? I was hoping that I will get some answers. Do you guys agree that when you add heat to a system, it will try to expand? Right? If you add heat to some gas, it will try to expand. Do you guys agree with it?
Yes, sir.
Okay. But of course, if you do not allow it to expand, if you keep the volume constant by using a rigid container or using a container with fixed walls, of course then all of that energy will go into internal energy, because delta W is fixed. Delta W is 0 because dV is 0. No work done can be done on the surrounding or can be done on the system because volume cannot change. But in a constant pressure process where you are not fixing the volume, you are fixing the pressure. It's just like the boiling that you do in your pressure cooker at home. Okay. Or let's say you have a container in which the upper wall can move if the pressure inside becomes large. So you try to heat it, your upper wall will move so that the pressure remains constant. Okay. But in a constant pressure process, any heat that you add changes the enthalpy. Now let me show you what is the difference when with the heat you add changes the internal energy, and the heat that you add changes the enthalpy. Let me give you the difference. Let's say you add 100 joules of energy to a system where the volume was fixed. So it means there would be a positive change or 100 joule change in your internal energy. But when you add 100 joules of energy at a constant pressure process, the change in internal energy would not be 100 anymore. Why? Because the sum of the energy that you added to your system went into expanding the gas. The volume will increase, right? It means when the gas expanded, the gas did some work on the surrounding. Do you guys agree? So this is, you can think of it this as that you give 100 units of food to this guy, and this guy does nothing. Why? This is not doing any work. So he eats this 100 units of food and it raises its internal energy. But this guy, when you give it 100 joules of energy, it does some work by lifting its, or let's say expanding the gas. You see, that is some work done on the surroundings. So it means, let's say, it does 30 joules of work. This is work, PV. Of course, you change your volume. So DH, so you see, DH is equal to, has some work in it. Okay, because in a constant pressure process, your dP is 0. Okay, so your change in enthalpy is equal to change in internal energy plus some work done. And you see, if the work done is negative, why work done is negative? Because the work is done on the surrounding. So V is positive, dV is positive because you increase the volume. So P dV. In this case, remember, because the work done on the system is positive and work done on to the surrounding is negative. So this is why the work is taken as minus P dV here. So a positive, this we will get up. Of course, your pressure will remain constant and your volume will increase. So you will get some work done on the surrounding. So once you do some work on the surrounding, so it means not all of your energy is going into changing the internal energy. So it means du must be 70 then. Let's say if this is 30, this is 0, of course, dp is 0. So it means the gas is doing some work on the surrounding. So this, if this is 30, then this must be 70. Why? Because we know that ds is equal to del q. Remember, in a constant pressure process, dh is equal to the amount of heat you add. So the dh is always 100. Why? Because you added 100 joules of energy. So if this is 30, this is 70. It means I can easily say that in a constant pressure process, the change in internal energy is less as compared to the constant volume process. Do you guys agree with it? If you do have any question, raise hand or speak. If you are confused, please raise hand. Because beta, in a constant volume process, all the energy went into internal energy. Here, not all the energy went into internal energy. Why? Because let's say the process, the process is a constant pressure process, so this goes to 0. So any heat that you add, which changes your enthalpy, it means, let's say 30 of it was used to do some work on the surrounding, and 70 is added to your internal energy. So now if your 70 is added to your internal energy, it means the amount of dt, the change in temperature, will be smaller here. Why? Because the change, internal energy change, was smaller as compared to here. That this is, let's say if this dt is 10, this dt must be 7. Why? Because this was 100 joules of energy directly went into internal energy, but only here 70 went. So it means this temperature change must be 7. Do you guys agree? Do you guys agree with this? Oh, I'm sorry. Yes. So this must be 7. Then, of course, we added the same amount of heat, 100 and 100. So this means if dt at a constant pressure process is smaller, so it means Cp must be larger, so that I get the same answer, 100. So bottom line is that in a constant pressure process, the amount of heat that you add not only changes the internal energy, but it also does some work on the surrounding. So it means the change in internal energy is less. So it means dt is less. So it means Cp has to be larger than 1. If you do not understand this, please let me know. I will repeat. Otherwise, I'm moving on. Okay, now let's go to the last topic of today. That is the entropy. You commonly understand entropy as the disorder or the chaos. So now let me give you an example. Suppose you have coffee in a flask, and flask is an isolated system. The heat cannot travel in, and the mass also cannot travel in or out. It's an isolated system. Suppose you have an ideal flask. What is an ideal flask? Ideal flask means you put some hot coffee in your flask and it will remain at the same temperature forever. Why? Because it does not lose any energy, right? So of course it has some air molecules inside, it has some liquid molecules inside, and they have some energy, they are moving, and their energy remains the same because they are not going to be losing any energy, because you have an ideal flask. It does not have any leakage. So of course this system of, the system which is, coffee, has some randomness, because the volume, the molecules are just moving randomly. It has some randomness, but that randomness does not increase or decrease, right? Because the volumes are there, the molecules are there now, they are not going anywhere, they are not losing their energy, so that randomness stays fixed, it does not increase. Now suppose you have another flask, but that is not ideal, so you put the same coffee in, but that is not ideal flask, so it means some of the air molecules inside will go out and some of the air molecules from outside will go in. So it means the temperature of your coffee will come down after 3 or 4 hours. That is what happens in real life, right? Okay. So it means, let's say you had 100 billion, let's say 1 billion molecules inside in an ideal flask initially. So of course, in a non-ideal flask, you also have 1 billion molecules of coffee and air and everything. But the problem with non-ideal flask is that those molecules are going to go outside. So the problem with those molecules are, the air molecules are, that they are going to go outside and they are just going to go away from each other, and they will keep on going away from each other. Now, if I want to track that system, it is going to become difficult and difficult with time. Why? Because the molecules which were initially inside come out, because those are the ones which are carrying my energy. The energy that was initially in the flask was in form of those molecules and air molecules and coffee molecule. But let's say those air molecules are coming outside now. Let's say if I want to keep track of all the molecules which were initially inside the flask, this task is going to become more and more difficult with time. Why? Because those molecules are going to go away. So it means I cannot track those molecules anymore. You see what I'm trying to say? It means my entropy is increasing. Why? Because after some time, when the time is passing, the number of possibilities or the number of arrangements or the number of places where my molecules went to is becoming more and more. Of course, when, let's say, when the one molecule comes outside from your flask, it can go on right, it can go on left, it can go on top, it can go on bottom, it can go straight. So these are all the possibilities for it. Of course, not only one molecule comes out of, of air. You can have a lot of molecules coming out of, condensation of the water vapor. All these molecules can come out and they can go anywhere. So with time, the number of possibilities of, the number of possible arrangements or the number of possibilities is increasing with time. So it means the number of disorder is also increasing. So this is called, my entropy is increasing. But in an ideal flask, my entropy will remains fixed. Why? Because all the molecules which were inside, of course, they can also move and they can have a lot of possibilities. But those possibilities or those arrangements are fixed. What I'm trying to say is, let's say you have a molecule A and B and C in your flask. The flask is ideal. They are not going to leave the flask. They are never going to leave the flask because this is an ideal flask. So molecules A and B and C, they are always inside. Of course, they can move in many possible arrangements. A can go on right, A can go on left, B can go on top, C can go over there. So of course you can have many possible arrangements and combinations, but those combinations are limited. Why? Because the volume is fixed and the molecules are fixed. So whatever those combinations are, of course, those combinations are very large because you have very large number of molecules in a fixed space. But remember, there may be a billion molecules inside, but the possibilities in which they can arrange themselves are limited. You see what I'm trying to say? Let's say you had 3 molecules, you can only arrange them in 6 ways. But of course, if you increase their volume, now they can arrange themselves in many different places. So the number of possibilities are going to increase. So the number of possibilities in which your system can arrange itself or the system can exist is actually your entropy. If the number of possibilities or the number of arrangements remains fixed, entropy remains fixed. But in a real flask where your molecules are going out, so the number of possibilities or the number of arrangements in your system, or you see your number of arrangements are increasing. Why? Because the molecules which were initially part of your system are going outside, and they can take many places. They can leave your room, they can leave your university, they can leave the city, and the entropy will keep on increasing forever. So this is why when you lose some heat, when there are heat losses, it means your entropy was increasing. The heat which was originally part of your system has left your system now, and it is going in many places, and with time the number of possibilities where it can go is going to increase, and of course that will increase your entropy. Do you understand the concept of entropy now? Before I read all of this, I wanted to have I wanted you to have wanted to have this discussion with you so that you can understand what entropy is. Entropy is a concept of statistical mechanics. It's not a concept of thermodynamics. In statistical mechanics, entropy is defined like this. Entropy is the number of possible arrangements in which your system can exist. So in an ideal flask, if you have a billion molecules, so there are extremely large number of arrangements possible, but those arrangements are fixed because the volume is fixed and the molecules are not leaving the system. But in a real flask, where in a non-ideal flask, when we know that the moisture and the air molecules are going to leave our flask, there are going to be some leakages and they are going to leave out the flask and they're going to leak into environment. So in that case, the molecules or the vapor molecules which were originally part of your system have left now, and the number of possible arrangements or the number of possible ways in which they can move are going to be increasing with time because they are going to move away from each other. So this is why your entropy will increase. So any questions in this? Then I start reading this text I copied from this website, and I thought this is a very nice text. So this is why I copied it, and this is why it is in. This is why I put quotes here, inverted commas, so that I can tell you that these are not my words. I copied it from open textbooks, some website. Excuse me. So how do I define it? So entropy is the level of randomness of disorder of a system. It could also be thought of as a measure of energy dispersal of the molecules in the system. I just gave you an example. Entropy is a level of randomness, and it can also be thought of the energy dispersal of molecules in the system. Microstates are the number of different possible arrangements of molecular position and kinetic energy at a particular thermodynamic state. So of course, if your number of possible arrangements of your molecules is increasing, entropy is increasing. Any change that results in higher temperature, more molecules, or larger volume yields increase in entropy. Higher temperature means your kinetic energy is large, they can go to more places. More molecules mean you have more number of things that can rearrange themselves. And more volume means there are more number of places where your molecules can go. So your number of arrangements are increasing. So it means your entropy is increasing. So now I am not writing mathematical form of second law of thermodynamics. We will do that in next class, but we are going to loosely define it. The loosely defining means that the universe moves in the direction of increasing entropy. So your entropy is always increasing in this universe. So this is the reason why the heat flows from hot to cold, not from cold to hot. And this is the reason why You must have studied in your FSC that you cannot operate an engine with a single thermal reservoir, meaning that you can take energy here and convert all of it into work. It is not possible because we are living in a real world. In a real world, you have to have losses. In a real world, this would be your engine. You take some heat from a hot source, you convert some of it into work, and some of it is rejected to cold sink. So this is why efficiency of your engine is never 100%. It's always 30. So you get only 40% of work, and rest of the heat is rejected to the cold sink. So this is the reality. This is second law of thermodynamics. We are going to define second law of thermodynamics in more detail in next class. So in meanwhile, if you have any question, please let me know. Otherwise, this class is over. Okay, so if you do not have any question, we will meet next time. Thank you so much. Allah Hafiz.